All right, 6.1. So continuing in the realm of graphing, now moving into quadratics from absolute values, but a lot of the characteristics we learned with absolute value will carry over to quadratics. So our essential question is what is the effect of the constant a on the graph y equals ax squared? So we're going, what does that a value do to our graph? So before we jump into that, let's understand our parent quadratic function. So just the equation y equals x squared. Okay, so this shape here is called a parabola. Okay, some of you guys will call it a U shape. I can see how where you see that U shape. Our vertex, just like it was on the absolute values, is where the graph turns and goes the other way. An absolute value is more distinct because that's where the specific v, but ours is this point here. So we would say it is at 0, 0. Our axis of symmetry, same as it was in the absolute value. It's the line that cuts our graph in half. That one's a little off kilter there. Let me see if I can make it better. That one's much better. And remember, it is x equals the x-coordinate of our vertex. And then on this one, we have a minimum. Since our graph opens up, we have a minimum value. There's nothing that goes below that point there. If our graph opened the other way, which we'll see in a little bit, we will have a maximum. So maximum is the highest value, minimum is the lowest value possible. And so we would state that we have a minimum at y equals 0 in this case, because that is the y-coordinate of our vertex. Now we talked about a little bit about domain and range for the absolute values. Let's apply that same concept to a quadratic. So I want to see if you can come up with what is the domain of f of x equals x squared, and what is the range of f of x equals x squared. So that would be referring to this graph here. So go ahead and answer those questions. We'll have that discussion when we come back into class. All right, moving on. So given a little bit specifics about a. So graphing g of x equals ax squared when a is greater than 0. So when our a is positive. So a of x is either a vertical stretch or compression of what we call the parent function, which we saw f of x equals x squared. That graph opens upward when a is greater than 0, and the function has a minimum value that occurs at the vertex of the parabola. So just to reinforce this, the graph g of x, a of x opens up when a is greater than 0 or a is positive. And when the graph opens upward, the function has a minimum that occurs at the vertex and specifically the y value. All right, so let's look at some variations of our graph. So we have f of x, which is this one here, and then we have our g of x, which is now some value that is multiplied by a there. So vertex for it is still at 0, 0. We're down at this point right here. Our axis of symmetry for both of them, can't get that bottom correct, but is x equals 0. Then we have our minimum, because our graph opens up, and we would say a minimum at y equals 0. Now our domain, since we have no issues, just like with our absolute value, is going to be from negative infinity to positive infinity. We can also write it as negative infinity less than x less than positive infinity. You may also hear it said called all reals, written in symbol form like that, but the first two are the main ones that we want to work with. So this is interval notation or inequality notation. And then our range, written in interval notation, we start just like our absolute value. So I start down here. Well, we don't hit it down here at negative infinity. We keep going up till we hit our point. So our graph starts at 0. And then make sure we have the bracket because we need to include that point. And it goes all the way up to positive infinity. The other way you could write it is y is greater than or equal to 0. And let's look at number 4 here. So vertex, that point right there, so at 0, 0. Our axis symmetry is x equals 0. And then our minimum, again, because our graph is opening up, so we have a minimum at y equals 0. Domain, as you're going to see, stays a lot the same. Negative infinity, positive infinity, you can write as inequality notation. And our range, since it hasn't been shifted, stays the same as well. All right, so we want to graph the quadratic function using a table. So as we do this, to learn how to graph it, we have our parent function there. So what we're going to do is I'm going to do the first couple before you get started, and then you're going to fill in the rest of this. So I'm going to substitute negative 3 in. So I get 1/2 negative 3 squared. Negative 3 squared is 9, so that gives me 1/2 times 9, which becomes 9 over 2. Or to make it a little easier to graph, we get 4.5. So we'd go negative 3 and 4.5. Do the same thing with negative 2. Negative 2 squared is 4. 1/2 times 4 now is 4 over 2, which is just 2. So we get negative 2 and 2. And I will let you finish from there, and we'll talk about this back in class. All right, so now looking at g of x equals a of x squared still, but now when a is less than 0, so that gives us a negative in front. That tells us it opens downward. It is a reflection of the graph across the y-axis, or sorry, the x-axis. And so when a is less than 0, the graph of g of x equals a of x squared is open downward. The function has a maximum that occurs at vertex of the parabola. So it opens downward. Is a reflection across the x-axis. When the graph opens downward, the function has a maximum this time. That occurs at the vertex. And again, just like last time, the y value specifically. So as we look at number 6 now, so we have a couple graphs going on here. We're looking at the darker one. The lighter one would just be the reflection of our f of x. So that's our strict reflection. And then we've changed that inner value, which we'll talk about a little bit. But as you can see, our vertex, even though we are now opening down, that turn point that happens is right there still. And so our vertex is at 0, 0. Which means our axis of symmetry is still x equals 0. Now this should state a maximum at y equals 0 because our graph is now opening down. So this then would be our max height that we go. We don't go above that. Our domain hasn't changed, so write an inequality method. So it's negative infinity is less than x, which is less than positive infinity. And then our range, so we're starting down here, checking, and our graph does hit negative infinity. So this time we're going to go from negative infinity to, and where does it end at? It ends at our maximum, which is at 0, and that needs to be a closed bracket. You can also write this as y is less than or equal to 0. And let's look at number 7 here. Same deal, so there's our reflection. The graph we're looking at is our bigger g of x out here. Vertex is still at 0, 0. Axis of symmetry is at x equals 0. Again, we have a max at y equals 0. Domain is negative infinity to positive infinity. And our range is negative infinity to 0, or y is less than or equal to 0. All right, so your turn. Go ahead and substitute some values in. First one, we would go negative 1/2 times negative 3 squared, which would be negative 1/2. Negative 3 squared, we already saw, is 9. And so that gives us negative 9 over 2, which is a negative 4.5 for graphing purposes. So negative 3, negative 4.5 is going to be a little off the chart here. So I'll estimate it be right around there. Do the same thing with negative 2. And negative 2 squared is 4. Negative 1/2 times 4 is negative 4 over 2, which is negative 2. So I plot that. We go negative 2, negative 2. And we're starting to shape in. Go ahead and finish the rest of this table and then fill in the characteristics. Now, not only can we graph, we also sometimes have to write our functions or equations given a graph. So we can determine a function or rule for a parabola with this at the origin by substituting your functional form, which is y equals ax squared, for any other point on the parabola into the x and y, and then solving for a. So we want to write the rule for the quadratic function shown on the graph. First thing we want to do is choose a point. We want to choose something besides 0, 0, though. So in this case, we'll choose the point 2, 2. The reason if you choose 0, 0, 0 multiplied by anything is going to be 0, so you're going to get 0 equals 0, and that's not going to help you solve for a. So we want to start with our functional form. And we replace our values. Now this one says g of x, so that y can be replaced with g of x. It's all the same idea, and so we're going to replace, so that 2 goes there, and then our x value 2 goes there. And now we want to solve for a, so we get 2 equals 2 squared is 4, so we get 4a, divide by 4, and a equals 1/2. So then we get g of x equals a, which is 1/2, and then x squared. All right, so your turn here. So let's get through and set up. So let's choose a point. In this case, the given point that's nice there for us is negative 2, -8. And we want to start with this here. We want to substitute our values in, so we get -8 is equal to a -2 squared. We're going to solve for a now, so I get -8 equals 4a, divide by 4, and -2 equals a. So this time we get y equals -2 x squared, and that y should be a g of x because that's what we started with. And so we get g of x equals -2x squared. All right, so you have a quizzes that you need to complete. There's some room here to use a scratch paper if needed. Go and complete that. Do not forget to turn that in as well. And then your essential question is, how can you use the value of a to predict the shape of f of x, ax squared without plotting points? And then our assignment, I know I forgot to write it at the top there. It's going to be page 218, number 1 through 13. Odd, and again, I'll have copies of that for you as well.